Welcome to the class of Artificial Intelligence and Machine Learning, and I am Ram Nivas from Department of Electronics and Communication Engineering. In today's class, we will see about model evaluation. Model evaluation is the process of measuring how well a machine learning model performs to identify the best model for a given problem. So how can we evaluate this model? There are two main methods. One is holdout method and the second one is cross validation. In case of holdout method, the data is splitted into training set and testing set and train the model on training data and test it on unseen data. In cross validation, data is split into multiple paths or folds and the model is trained and tested multiple times, which gives more reliable results. So importance of model evaluation are it helps us to choose the best model, and many algorithms can be used for a problem. Not all give the good result, and evaluation helps to compare the model and find the most suitable one. So this is about help chooses the best model, and it improves accuracy. Accuracy is equal to the correct predictions per total predictions. If it is a high accuracy, then we can say our model is a good model. If our accuracy is less, then we can state that our model is a poor model. This is in terms of accuracy, and from the model evaluation, it is evident that our accuracy is improving, and it prevents overfitting. Overfitting happens when model memorizes training data but fails on new data. And following are the evaluation metrics of model. Evaluation metrics are the measures which are used to check how well a machine learning model performs. So the regression metrics are mean absolute error or MAE, mean squared error or MSE, root mean square error or RMSE or R squared error. So a mean absolute error is the average difference between actual and predicted value, and mean squared error is the average of squared differences, and it gives more importance to large errors. Root mean square error is uh, is the square root of mean squared error and error in same unit as output. And R squared error shows how well the model fits the data, and which is closer to 1 is better. So mean absolute square, this is the formula where yi is the actual value, yi cap is the predicted value, and n is the number of points. So the average difference between the actual and predicted values, which is summation of yi minus yi cap divided by n. The mean squared error is the average of squared differences, which give you one more squared in addition to the previous expression where yi minus yi cap the whole squared is given here. The rest of the formula is more or less same. And root mean squared error formula, you are introducing root to the previous formula, like square root of 1 divided by n, summation of it varies from 1 to n, and yi minus y cap whole square. And r square is 1 minus summation of yi minus yi cap square divided by yi minus y bar squared. So this is about the four different regression evaluation metrics. Now we'll see a problem on it, and the student 1, 2, 3 are given, and their actual values are given, predicted values are given, as well as the errors are given. Now finding out the mean absolute error, the error value is taken as whole. It is not considered with the minus sign. So mean absolute error is equal to 5 plus 2 plus 5 divided by, there are 3 students, so divided by 3, which is equal to 4. The model makes an average mistakes of 4 marks. This is what we have concluded. In the mean squared error, 5 squared plus 2 square plus 5 square, which is nothing but 25 plus 4 plus 5 divided by 3 students, which is equal to 18. Here I have given it as 18. There is a chance that you might get from floating point values. So this gives importance to bigger mistakes. And then root mean square error is nothing but 18 square, which is nothing but the square root of mean squared error. As a result of this, I am getting a result of 4.24. Now r squared error is computed 1 minus 54 divided by 200, which is equal to 1 minus 0.27, which is equal to 0.73. Which is nothing but the direct substitution of values. You can expect these type of problems in your semester examinations. Like, next is confusion matrix. So confusion matrix is the matrix which is drawn from actual values and predicted values. If both the conditions are true, then it is true positive. If both the conditions are false, then it is a true negative. Here we can consider a parrot and not a parrot. When two actual and predicted are parrot, then it is a true positive. When actual and predicted are not apparent, then it is a true negative. If any one is positive and the other is negative, means we'll get false positive and false negative. So true positive is nothing but correctly predicted positive value, and true negative is nothing but correctly predicted negative value, and false positive is incorrectly predicted positive value, and false negative is incorrectly predicted negative value. So from this, there are a few four other parameters like accuracy, precision, recall, and F1 score. They can be derived from true positive, true negative, false positive, and false negative. Accuracy is the proportion of correct predictions, and precision is out of predicted positive, how many are actually correct, and recollect is out of actual positive, how many are correctly predicted, and F1 score is nothing but a single value that balances precision and recall. This is the formula for computing accuracy, precision, recall, and a F1 score. Accuracy is the measure of proportion of correct predictions by the model out of total number of predictions. So here the correct predictions, we know that total positive and total negative. Okay, true positive and true negative divided by true positive, true negative, false positive, and false negative. Because this false positive, false negative, true positive, true negative together form the total number of predictions. Okay, so in the precision, focus on proportion of true positive value predictions out of all predictions made by the model. So true positive divided by true positive and false positive, because these are the only true positive contents here. Next is recall. Recall is also called as true positive rate or sensitivity. Recall measures the proportion of true positive predictions out of all actual positive instances. So the recall is equal to true positive divided by true positive false plus false negative. So there is a difference from precision and recall. You need to understand this. So F1 score is the harmonic mean of precision and recall. It combines precision and recall into single value, where high F1 score indicates better model performance, where F1 is equal to 2 into precision into recall divided by precision plus recall. Now we are given with a question like true positive is 80, true negative and false negatives are 10 and 20, and true negative is 290. The medical diagnostic test, the model is used to predict whether a patient has a certain disease or not. The confusion matrix will be given in your examination. Now you can substitute the values directly for accuracy, precision, recall, and F1 score. As a result of this, you will get the accuracy of 92%, precision of 88.89%, recall of 80%, and F1 score of 84.22%. So train and test data are given. So training data are more when compared to that of testing data. So in a data set, you need both training data and testing data. From the original set, we can categorize them to training data and testing set. Training data performs training, tuning, and evaluation, and it is fed to the machine learning algorithm followed by predictive model. From the training set, we can have another one categorization like validation set, which is useful for validating our inputs, and it is happening cyclic process as shown in this figure. And the test set is given to the predictive model for evaluating the final performance estimations. Now we'll study about the cross validation, which is a technique used to check how well a machine learning model performs on unseen data while preventing overfitting. It works by splitting the data into several parts, training the model on some parts and testing it on the remaining part, repeating this resampling process multiple times by choosing different parts of the data set, and averaging the results from each validation step to get final performance. So this is the block diagram of k-fold cross-validation. So scuffle data set, it is given to split data sets into training and testing set. Split training data set into k-folds, use k minus 1 for training, and always leave one fold for test and take care of transformation in the fold and find the accuracy of each fold. So bias and variance trade-off. In machine learning, prediction accuracy depend on two types of errors. One is bias and variance. The balance between these two is called as bias variance trade-off. Bias occurs when model is too simple. Model does not learn patterns properly. It makes incorrect assumption about the data, and errors are high in both training and testing set. The situation is called as underfitting. Higher bias means model is too simple, and variance occurs when model is too complex and model learns training data too closely. It performs very well on training data. It performs poorly on new data. This situation is called as overfitting. High variance means model is too complex. So this is the diagrammatic representation of model complexity versus original model complexity, representation of total errors, variance, bias, square, and error. So simple model, high bias and low variance. Complex model, low bias and high variance. Both cannot be minimized at same time. The goal is to find a middle ground, not too simple, not too complex. The best model is one that balances bias and variance. So this balance gives the lowest error on both training and testing data. The total error is equal to bias square plus variance plus irreducible error. So error from simplicity, error from complexity, noise that cannot be removed. So overfitting and underfitting, which we have discussed in the previous classes. If a model learns too little, then it is underfitting. If a model learns too much, then it is overfitting. Underfitting happens when model is too simple and fails to learn important patterns, poor performance on training data, poor performance on test data. And causes are model is too simple, high regulation, missing or weak features, not enough training, and high bias. And bias variance in underfitting, high bias, low variance, and underfitting, high bias plus low variance. This is the formula for it. Now, when you are coming for overfitting, it happens when model is too complex and learns noise along with real patterns. Very good performance on training data, poor performance on testing data, because it is performing well on training data. It has mugged up the data from training data. So underfitting, overfitting, and appropriate fitting. This is the graph. So in uh, overfitting, high bias, low bias, low underfitting we have high bias. In good fitting we have low bias and low variance. In overfitting we have high variance. Good fitting, the graph is smooth and it is having a good transition. But in high bias it is very linear, and in high variance it is not in a proper format, that is not smooth like good fitting. So that's it about today's class, and thank you.